true hues of the cosmos, beyond the black and white screen. Welcome, space enthusiasts, to a journey that will redefine how you see the universe. For decades, our perception of space has been largely shaped by the monochrome images from early telescopes, or the vibrant, often artistic, interpretations we see in science fiction. But what if I told you that the cosmos is bursting with colors far more subtle, complex, and scientifically profound than you've ever imagined? Forget the simplistic black void dotted with white stars. Space is a canvas painted with light, not just visible light, but across the entire electromagnetic spectrum, revealing a breathtaking palette that tells the story of cosmic evolution. Today, we're diving deep into the science behind these real colors, exploring how astronomers capture them and what they truly reveal about the universe around us. Prepare to have your mind and your eyes opened. The rainbow of light, electromagnetic spectrum. To understand the true colors of space, we first need to grasp the nature of light itself. What we perceive as color is merely a tiny sliver of the electromagnetic spectrum, the visible light spectrum. But light extends far beyond red and violet, encompassing radio waves, microwaves, infrared, ultraviolet, X-rays, and gamma rays. Each of these wavelengths carries unique information about celestial objects. When astronomers talk about color, they're often referring to the intensity of light detected at specific wavelengths, not just what our human eyes can see. Our instruments allow us to see in these invisible light ranges, translating them into colors our brains can process. This scientific coloring process isn't arbitrary. It's a carefully calibrated method to reveal the hidden properties of the universe, from the coldest dust clouds to the hottest, most energetic phenomena. Why space appears black, mostly? If space is so colorful, why does it mostly appear black to us with the naked eye? The answer lies in the vast emptiness between celestial objects and the way light travels. On Earth, our atmosphere scatters sunlight, making our sky blue. In the vacuum of space, there's nothing to scatter the light from distant stars and galaxies, so the light travels directly to our eyes. While there are countless stars, they are incredibly far apart, and their individual light sources are too dim to illuminate the vast stretches of space between them, enough for our eyes to perceive a glow. Furthermore, light diminishes with distance. So, unless you're looking directly at a star, planet, or nebula, your eye perceives the absence of bright, scattered light as black. It's a perception, not an absolute truth about the color of the void itself. Nebulae. The cosmic paint palettes. Nebulae are perhaps the most vibrant and visually stunning objects in the cosmos, often appearing like celestial artworks. These are vast clouds of gas and dust, and their colors are incredibly informative. For instance, the brilliant reds in many emission nebulae, like the Orion Nebula, are often due to ionized hydrogen atoms. When hydrogen atoms are energized by nearby hot, young stars, their electrons jump to higher energy levels. As these electrons fall back down, they emit light at very specific wavelengths, with red being a prominent one, specifically the H-alpha line. Blues, on the other hand, often indicate the presence of ionized oxygen, while greens can be attributed to doubly ionized oxygen. Different elements glow at different wavelengths, acting as cosmic fingerprints that tell astronomers exactly what these stellar nurseries are made of. Galaxies. The grand tapestries. Galaxies, those colossal islands of billions of stars, gas, and dust, present a different kind of color story. Their overall hue is a magnificent blend of the light from all their constituent stars, along with the glow of nebulae and the scattering of dust. The iconic spiral arms of galaxies like our Milky Way often appear bluer due to the presence of hot, massive young stars that burn brightly in blue-white light. These are regions of active star formation. The central bulges of spiral galaxies and elliptical galaxies tend to be yellower or redder because they are dominated by older, cooler stars, which emit more of their light in the red and yellow parts of the spectrum. Dust lanes within galaxies can appear dark, but they also scatter light, sometimes lending a reddish or brownish tint. Each galaxy is a unique, colossal spectrum of light. The true rainbow makers. The color of a star is a direct indicator of its surface temperature, and by extension, its mass and age. This is a fundamental concept in stellar astronomy. The hottest stars, often massive and young, burn with intense blue or blue-white light, reaching surface temperatures of tens of thousands of degrees Celsius. Our Sun, a medium-sized star, is a yellow dwarf with a surface temperature around 5,500 degrees Celsius. As stars age and cool, they expand into red giants, appearing distinctly orange or red, with surface temperatures ranging from 2,500 to 3,500 degrees Celsius. These are not just artistic renderings. These colors are determined by the physics of blackbody radiation. Every star, from the faintest red dwarf to the most luminous blue giant, contributes its unique spectral fingerprint to the grand cosmic canvas. Cosmic dust, obscurers and illuminators. Cosmic dust, though seemingly mundane, plays a fascinating role in the colors we perceive in space. Dust particles can either obscure light or reflect it. Dark nebulae, like the famous Horsehead Nebula, appear as dark silhouettes against brighter backgrounds because dense clouds of dust block the light from stars behind them. However, dust can also scatter light, creating beautiful reflection nebulae, which often appear blue. This is similar to why our sky is blue on Earth. Shorter blue wavelengths of light are scattered more efficiently by the dust particles. Conversely, when dust is heated by nearby stars, it can re-emit light in the infrared, which, while invisible to our eyes, adds to the overall color profile when translated by instruments. Dust thus acts as both a cosmic curtain and a diffuser, shaping the visual tapestry of the universe. The role of filters in astronomical imaging. Since our eyes are limited, astronomers use sophisticated techniques to capture the true colors of space. One of the most crucial tools is the use of narrow-band filters. These filters allow only very specific wavelengths of light to pass through to the camera's sensor. For example, a filter might only allow the light emitted by ionized hydrogen, red, to pass, while another might let through light from ionized oxygen, blue-green. By taking separate images through these different filters and then assigning specific colors, often red, green, and blue, to each filtered image, scientists can combine them to create a full-color composite image. This process isn't faking the colors. It's a scientific translation, allowing us to visualize phenomena that would otherwise be invisible, revealing the elemental composition and energy states of cosmic objects. False color versus true color. The scientific distinction. It's important to distinguish between true color and false color images in astronomy. A true color image aims to represent celestial objects as closely as possible to how the human eye would perceive them if we were right there, albeit with significantly more light gathered. This is often achieved using red, green, and blue filters that correspond roughly to the sensitivity of our eyes. False color images, however, are a powerful scientific tool. They assign visible colors to wavelengths of light that are invisible to us, like infrared, ultraviolet, or X-rays. For example, in an X-ray image of a black hole, different energy levels of X-rays might be mapped to blue, green, and red to highlight variations that reveal crucial physical processes. This isn't artistic license, it's a method to convey complex scientific data in a visually understandable way, unveiling layers of information beyond our natural sight. the beauty and science of cosmic colors. So, as we conclude our colorful cosmic journey, remember that the universe is far from the monochromatic canvas many once imagined. Its true hues are a magnificent testament to the intricate physics and chemistry at play across unimaginable distances. From the brilliant blues of newborn star clusters to the deep reds of hydrogen gas and the subtle yellows of ancient stellar populations, every shade and tint tells a vital part of the universe's story. These colors aren't just aesthetically pleasing, they are scientific data points, revealing temperatures, compositions, velocities, and evolutionary stages of galaxies, stars, and nebulae. By understanding how astronomers capture and interpret these real colors, we gain a deeper appreciation for the breathtaking beauty and the profound scientific revelations hidden within the true spectrum of the cosmos. Keep exploring, keep wondering, and keep looking up.